Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hi, welcome to Physics with Beth and Beth. I'm Beth. We're in that AP Physics 1, Unit 7, Oscillations. This is the last video of this unit, and then our next video will be about Unit 8, the Fluids unit. So you are 7/8 of the way there. You are almost there. You've got this. So we are talking about simple harmonic motion problems today. And before, our videos have talked about concepts of graphing simple harmonic motion, taking a position versus time graph, converting it into a velocity versus time, or translating it into a velocity versus time, and then an acceleration versus time graph. So today we're talking about problems. On your AP Physics 1 equation sheet, you're going to see these two equations for position. All right, they look very similar, except one's cosine and one's sine. So we're going to have to talk about how do I know which one to use? And it's going to be, if they gave you a graph, you're going to know from the graph. If it starts at an amplitude point in the positive, so above the equilibrium line at an amplitude, this is a cosine graph. So we would be using this equation for cosine. All right, if it were to start at equilibrium and start here and then go up like this, then that is the sine curve. It's starting at equilibrium and going up to positive position and then down into negative position. All right, and then you would use this equation. Now, when you get to AP Physics C and you're doing calc-based, this equation is going to look a little differently. You're going to have a phase shift on here, and because you're gonna be just adding to it. And this is more of a two basic equations they're using for AP Physics 1, put it that way. So when you get to mechanics and calculus base, go, well, that's not what we learned in AP Physics 1. It's the same, they're just adding a little additional where you can start anywhere in this curve. All right, so we'll not worry about that yet. So I know I have given you this. Now, it may not be quite as easy as this. They may just keep going and have multiple cycles on one graph. Just know that you're looking from where it starts, goes down, and comes back up here. That is one cycle. I've just stopped it at one cycle for convenience in this video. All right, perfect. Now, I have a spring mass of 1.5 kilograms, and I tell you this is its position time graph. Now, we can totally overanalyze a spring, as I've mentioned in earlier videos, and this is no exception. It's crazy how much stuff you can figure out from just the mass in this curve, this graph. So let's get started. The first thing they ask for is period. Okay, period is the time it takes for one cycle. It starts here at 0 time. It ends here. If you can't read that, that's a 0.4 seconds. So my period is 0.4 seconds. Okay, and I'm going with 2 sig figs, so that's easy enough. It's also important to note that each of these little sections, there's 4 in this one cycle. So this is 1/4 of the cycle, this is 1/4 of the cycle, this is 1/4 of the cycle, and here's your last 4th. 1, 2, 3, 4. So 4 parts make a whole here. All right, so this is 1/4. So if it asks you the time it takes for this spring to go from maximum position to maximum position, so from its maximum compressed to its maximum stretched, all right, then how do I know that time? Well, it's from top to bottom. We'll look at that. That's 0.2. That's 0.2 seconds because it's a 4th and a 4th. Each one of these 4ths is 0.1 for this spring. So it's 0.1 plus another 0.1 seconds, and that would be 0.2 seconds. So if it asked you from compressed to stretched, how long does it take you? 0.2 seconds, because that's half the cycle. It's important to understand that. Okay, now the next thing they asked, we did period perfect, was amplitude. All right, amplitude is that max distance stretched or compressed from equilibrium. 0.5. Negative 0.5, it's 0.5. They're going to ask you for the magnitude of the amplitude because it could be 0.5 or negative 0.5. Anyway, it's 0.50 meters because remember that's a distance, maximum distance from the equilibrium line. Perfect frequency, they want to know frequency. Well, frequency is 1 over period, which would be 1 over 0.4 seconds. So frequency equals 2.5 hertz. Awesome. Now they ask for angular frequency. All right, angular frequency we remember is one cycle over the time it takes for one cycle. All right, or it can also equal 2 pi frequency, because we know frequency is 1 over t. It doesn't matter which one you use. I'm doing the period, so that would be 2 pi divided by 0.4 seconds, and that's going to give you an answer of 15 point, where'd it go? It gives you an answer, sorry, 15.71 radians per second, because remember, angular frequency is radians per second, so 15.71. All right, cool, we got angular frequency done. Now they want mechanical energy. All right, remember mechanical energy is, we talked about this in the last video, that at the top of an amplitude, there's no velocity. That means it's all potential energy, because the spring stops to turn directions, and it starts at rest, it stops here to turn around, to turn directions. This would be keep going for another cycle. It would stop to turn directions again. All right, so mechanical energy at this amplitude equals the potential energy of the spring, because there's no kinetic energy, because velocity is 0. So it's all potential energy. So we call that, you could call it x max squared, but we really refer to it as k. That max we know is amplitude squared. All right, that's going to be your mechanical energy, which is 1/2. K we do not have yet. Our amplitude is 0.5 squared. So you're like, how do I get k? All right, well, and k is the spring constant, right? So we're going to calculate the spring constant. So our spring constant, remember, is period of a spring equals 2 pi, and let me just drop down a little bit, because we're going to come back and fill this in, because we're like, oh, wait a minute, you asked for mechanical energy, but I don't have my spring constant yet, and I've got to go find that, and that wasn't up here to find, but I have to find it in order to get mechanical energy. So I'm going to say that my period of a spring equals 2 pi, the square root of mass over my spring constant. We also found in an earlier video, which I derived, if you want to go back and look at that, that your angular frequency equals the square root of k, the spring constant, divided by mass. You could use either one of these, you'll get the exact same answer. I'm just going to use this one because it's on your equation sheet. I know my period is 0.4, I have 2 pi, and I have square root of 1.5 over my spring constant. All right, you're going to divide both sides by 2 pi. You're going to have to square both sides, because a square of a square root is just what's underneath. And then you can solve it. All right, if I did this, I'm just going to go ahead and write in some numbers. 0.06366 equals the square root of 1.5 over the spring constant. 1.5 is the mass. What I did was just divide both sides by 2 pi. Now I'm going to square both sides, because that square root squared is just what's underneath it. So this is 1.5 over k, and this becomes like 0.004053. I solve for k by multiplying k, dividing this huge number, 1.5 divided by this huge number, and you're going to get a k of 370 spring constant, newtons divided by meters. Now I have a k, and I can plug that in here, and I get my mechanical energy. All right, so my mechanical energy is 1/2 that 370 times my 0.5 squared. So my mechanical energy is going to equal 46.25 joules. And wow, I barely gave myself room for that, but 46.25 joules. All right, mechanical energy's done. We're getting there. Now maximum velocity. Ooh, okay, so we know at the amplitudes we have only potential energy because velocity is 0. Well, at the equilibrium line, our x is equal to 0. So our potential energy is equal to 0, and it's all kinetic energy. So at our equilibrium line, kinetic energy is a max. All right, that means our velocity has to be a max at that equilibrium line too. And again, why is that? Because the potential energy of a spring is 0. We know that potential energy of a spring is 1/2 spring constant times x squared, but at equilibrium, x is 0. So no potential energy, all kinetic. And we are ignoring friction, by the way, on all of these. Okay, so now we're going to find that max velocity. All right, well, we know that our kinetic energy max is 1/2 mv squared, and that would be when velocity is a max. All right, well, kinetic energy is a max, we said at the equilibrium line. It's all kinetic energy. That means all of your mechanical energy is kinetic energy. Just like at the amplitudes, all of your mechanical energy was potential energy of the spring because velocity was 0. So kinetic energy is going to be max when it equals your total mechanical energy. I know my total mechanical energy is 46.25 equals 1/2. My mass is 1.5, and that's my velocity max squared. So we're going to multiply by 2, divide by 1.5, take the square root. We've become masters at all of this algebra at this point, so I'm just going to tell you that the velocity max is 7.85 meters per second. All right, and there you have everything we've asked for so far. We have period, amplitude, frequency, angular frequency, mechanical energy, the spring constant, and your velocity max for this spring. Now they're going to come around and say, hey, okay, now at 0.15 seconds, I want to know what the position, the kinetic energy, the potential energy, and the velocity is. Okay, so we got to think about this. 0.15 seconds. Here's 0.1 second. Here's 0.2 seconds. So at 0.15, I'm somewhere here, somewhere in between your equilibrium line and your amplitude here. That means I am in a negative position. So I know I should be coming out with a position that's negative. That's a great check. If I had said I was between 0.3 and 0.4 seconds, then that means I would be somewhere here. And I would be in a positive position. All right, somewhere. So those are excellent checks to do. We've already said this is a cosine, so I am using x equals my amplitude times cosine times 2 pi, my frequency, and that's frequency in hertz, times the time that they want me to find this, and that's 0.15. Here's a big, big, big note. Like, star it, I don't care how many times, you can't star it enough. All right, for these problems, you need to be in radians. You must be in radians, okay? This whole little guy thing here is radians. So you have got to be in radians because look, 2 pi times frequency, that's angular frequency. We said that earlier, that angular frequency is 2 pi times regular frequency. That is angular frequency. That means that is radians per second. You're multiplying by another second. So you are in radians. You have got to hit your mode on your scientific calculator and switch from degrees to radians. Now, most of this, in fact, the entire year up to this point, you've been in degrees. So when you are taking the AP exam, you need to be in degrees to start with, but anytime you have a simple harmonic and you're using these two equations, you need to stop, change your calculator to radians, and do the problem. Then remember, oh, okay, I gotta go back to degrees now if you're for other problems, okay? So that's really important that this guy, that your calculator needs to be calculator. I'm talking and not writing. There you go. Your calculator needs to be in radians, not degrees. All right, so we're going to get started. We're going to find position first at 0.15 seconds. My amplitude we know is 0.5. I'm going to do cosine of 2 pi times that frequency, and I'm going to do a square bracket here. That frequency was 2.5 hertz, and my time is 0.15. All right, where did I get my time? They told me. Find position at 0.15 seconds. All right, when you do that, you're going to take 0.5 and you're going to have a cosine. When you do that, you get to a cosine of 2 I'm going to write this in so you can make sure you're in the right mode on your calculator. It's 2.3562. Now you take cosine of that times 0.5 and you're going to get a negative. And we said we should get a negative. We're between 0.1 and 0.2 seconds. That means we need to be a negative, and you get a negative 0.354 meters. There's the first part. Done. Now they want the kinetic energy, the potential energy, and the velocity. All right, well, the next thing we're going to do is potential energy. So I know that my potential energy is 1/2. The potential energy of a spring is 1/2 my spring constant times the distance stretched or compressed. Well, I know my position now. All right, so that potential energy is going to be 1/2. The K was 370. And I have a negative 0.354. Do not forget to square that. We square position. And your potential energy of a spring is going to be 23.13 joules. All right. Well, we know our total mechanical was 46.25. So we are almost exactly halfway between our equilibrium and our amplitude. All right, now the next thing they ask for, that's done. They want kinetic energy. I'm going to go ahead and erase all of this so that we have some room to work. All right, and I know that my mechanical energy equals my kinetic energy plus my potential. I am between equilibrium, which is all kinetic, and amplitude, which is all potential energy of the spring. I'm in between. That means I have both. I know my mechanical energy is 46.25. I'm looking for that kinetic, and I just found my spring potential energy of a spring, which was 23.13. All right, so that gives me a kinetic energy of 23.12 joules. Now they want the velocity at this point. Well, if I know my kinetic energy, I can find my velocity, because kinetic energy is equal to 1/2 mv squared. My kinetic energy is 23.12. My mass is 1.5, and I'm looking for that velocity at this time of 0.15 seconds. And if you multiply by 2, divide by 1.5, take the square root, you get velocity of 5.55 meters per second. All right, now it's also important to understand that to check, you know your maximum velocity, we had just calculated it, was 7.85 meters per second. We're less than that. You can't be over your max, right? Because we're not at the equilibrium line. So it needs to be something less than that, because our kinetic energy is getting converted as it goes to potential energy of the spring. So anyway, that is how you do a simple harmonic problem, simple harmonic motion problem. And we can ask you all sorts of things. Lots of parts, A, B, C, D, and on. All right, but I hope that helps. If you like this, give us a thumbs up, share with a friend. We would love for you to subscribe, and we have new videos coming out on that fluids unit, unit 8. And happy physicsing, and thank you for watching.